Thanks so much, Mala and Kathy, for putting this on. Super excited to be here today, and thank you for spending part of your Friday to watch this session. Before we get started, I wanted to do a quick call out to our sponsors so I don't forget at the end. It's really great what the community does, what our sponsors do, how we can build this community. I've never actually been a part of a community that is so strong and supportive of one another. So it's just really great to see these sorts of things and to get to participate. If you're not involved in the Women in Tech community or other communities that we have, I would definitely recommend joining them when you can. They're great. A little bit about me, just since this is kind of a beginner's data science day, I wanted to share just my journey for data science. I thought that might be useful for you all. So I actually studied engineering in university, but not computer engineering or data science or anything like that. I studied materials engineering, and then I started as a consultant at Microsoft, and I ended up working on a bunch of telemetry gathering and data ingestion and Power BI stuff. And I realized, wow, I really kind of like this. So I investigated some programs that Microsoft had for free or very little money. At the time, it was called the Microsoft Professional Program for Data Science. Now they have other programs, and I'll share how you can get involved with those and how you get some discounts. But basically, my goal was to try to get some sort of certification so that I could do more data science projects. And then once I finished that, I realized I hadn't quite itched the scratch that I had for data science. So I looked into different university programs, and there are a bunch of programs out there that are online that are relatively inexpensive. I ended up going back to my undergrad's university at Georgia Tech because they have a very inexpensive program. It's about $10,000 for the entire degree, whereas most other schools I looked at were between $10,000 and $35,000 per year, and it takes a few years to get this thing done. So if you're thinking about going back to school, you went through today and you're like, oh, I'm really excited about data science, I want to go take some classes, I would recommend Georgia Tech and University of Illinois Urbana-Champaign. They both have these really low cost programs, but they're both two of the best computer science programs in the United States. So if that's something you're interested in, you can also always find me on Twitter or LinkedIn or something, and I'd be happy to chat about it. But today I wanted to give a behind the scenes look at AI, machine learning, and deep learning through the eyes of a data professional. So getting into it, what I want to talk about today is kind of the progression of different things that we've seen in history as well as in practice, kind of give you an overview, and I'm hoping you'll walk away with a better understanding of what the differences are between these different things, as well as some of the tools that are available, as well as like some of the tech that you can use depending on your experience or skill level or desire to get hands-on with machine learning, AI, and deep learning. There are things available. So hopefully you walk away today, regardless of your skill level, with something you can use and apply in your day-to-day. That's kind of my goal. So let's go ahead and get started. I want to start by talking about data science. I know it's the end of the day, so probably you already have like some idea of data science, but the way I like to describe it is to talk starting with data analysis. Now, these are things that I think as a data professional, you probably have a lot of these skills, right? We start with create, read, update, delete, programming, reporting, data engineering, that sort of thing, storytelling with your data, using things like Power BI to kind of present your results. But then there's one other side of that, and that's kind of the scientific side. And if you're familiar, maybe way back in school, you learned about the scientific method, where you basically define a question, you create a hypothesis, and then you try to test that hypothesis to either prove it true or to reject that hypothesis, say it's wrong. And then there's usually like some action that happens. Maybe you're going to publish your results. Maybe you're going to change the study or the way that you do things. So data science is kind of the combination of these things: data analysis, scientific process, and then this third item of artificial intelligence. And under artificial intelligence, there are kind of two things that we'll dive into today, and that is machine learning and deep learning. So a lot of this are things you probably already know, and then the artificial intelligence is where we have space to grow. Now, I don't know about you all, but I am super big on process, right? I like to do things that are repeatable. I like to know I have a structure to follow. And so a few years back, Microsoft actually created a product group to create something called the Team Data Science Process. And I put a link there in the bottom left, the TDSP. And Microsoft took this very seriously, said this is a product, so we need to define it very well. And there's all sorts of documentation and videos. But basically what they did is they gave us a structure, and there's all sorts of resources there, but they gave us a structure to follow any data science project. So if we think about kind of that process briefly is, when you think about a data science project, the first thing you need to do is understand the business. What is the business understanding, and what is kind of the challenge that we hope to address or solve or make better with data science? So that's kind of the first big thing. We have to have some business understanding. After that, we need to go look at the data and figure out, what do we have? Is it going to help us with the business understanding or the question we thought we wanted the answer to? What's the data source? What's the pipeline? What's the environment? And here's where a lot of that data engineering comes in, and cleaning data. And regardless of what any data scientist tells you, this is where you spend most of the time. So the good news is, as a data professional, these are all things you're probably already very comfortable with. So you're really way ahead of most people just getting started with data science. Now, what you'll notice is that the arrows between all these steps go both ways. So, after you go look at the data, you might say, oh, well, this kind of changes what we understood about the business, and this kind of changes the question that we want answered. So, know that at any point you might go backwards or forwards or cycle back to an earlier phase. And that's okay. That's actually encouraged, right? You don't want to just press on. You want to, they say kind of like fail fast, not that you're failing here, you're learning, but fail fast and pivot so that you can get to the root of whatever it is that you're trying to improve or accomplish. So after the data acquisition and understanding, the next thing is to start creating some models. So figuring out which features, we'll talk about what features are, but which features are important, and doing your training, your testing, evaluating your models, and then deploying your model to production. Now, over time, you might need to update this model. And that's why, again, you might go back to data understanding, you might go back to modeling, and then redeploying that model. So we're going to talk more about these, but I thought this was kind of an important structure to say up front. So that being said, I want to take a step back in time and look at history. So let's take a look at history. And again, I think I might have mentioned this at the beginning, but I do want to say, I do have the chat window open. So if you have questions, comments at any point, please go ahead and put them in there. I'd be happy to address them. All right, so let's take a look back in time and go back to the 1950s. Now, in the 1950s, this is really when the term artificial intelligence started to become used. And what scientists and mathematicians then kind of said is, hey, we're pretty good at computers, so we can figure out pretty much anything that a human might want. So for example, if you have a kid and you want to know what they want to order at a fast food restaurant, it's obviously going to be a burger and not a salad. So basically what folks said working in artificial intelligence at the time said, people are really predictable. So we can easily quantify anything that a human thinks. So tried a lot of things. We'll talk about how they tried those things. But then there was a time where they realized it wasn't quite as easy as they thought it was going to be. And we had something called the AI winter. So things went dormant just for a little while. Now, back in the 1980s, something called data mining became much more popular. So this idea of using statistics to make predictions from larger sets of data, because as time goes on, our compute power and our ability to store data has also improved. So this is when we started combining symbolic logic with machine learning and data mining. So kind of putting these things together to kind of mature more in the machine learning space. So this happened up until the early 2010s, and you could argue is still happening today. And then what happened around the 2010 time is we started getting more involved in something called deep learning. So basically leveraging layers, and we'll talk about what those are, to do more complex computations and to handle more data. And you'll kind of see this theme overall, and we'll talk a little bit more about it. But in my opinion, and I think a lot of folks would agree, the big thing that has changed is really compute power and our ability to store and process data. So that's really what's driven us to be able to do things like deep learning. Different computations that would have taken, weeks to compute and process all that data can now be done, in a matter of minutes with the existing technology that we have. We'll talk a little bit about that technology too. So before we dive into the difference between AI, ML, and deep learning, I wanted to give some spoilers. So sorry. But, if you think about it as like these, areas, artificial intelligence to me is like the biggest area, right? This is mimicking any human behavior. That's the goal. And we'll talk about some of the different ways that we did that throughout time. Then you have this kind of subset machine learning where we're actually giving data to machines and looking at them and looking for them to kind of learn the trends and patterns and be able to make predictions. But again, it's still all part of this bigger subset of artificial intelligence because we're mimicking human behaviors and human capabilities. Now, if we go one layer deeper, deep learning is a very specific type of machine learning or subset of machine learning that uses neural networks. And we're going to look at a neural network. We're going to dive really deep into a neural network for some not so deep learning. So we'll talk about that as well. Now, I mentioned about the data that we have available and the compute power that we have available. The reason this is important is because a big difference between machine learning and deep learning is that at a certain point, a machine learning model tends to level out after, it gets enough data. After a certain point, it just kind of levels out. Whereas with deep learning, typically and in practice, the more data that you are able to get and leverage, the better your performance of that model that you create turns out to be. So this is another reason why deep learning has, increased in popularity over the recent years. All right, so now that you've had the spoilers, let's talk about each of these. So we'll start with artificial intelligence. So I kind of explained this earlier. In the 1950s, there was a Dartmouth summer research project, and they said human intelligence can be so precisely described that a machine can be made to simulate it. So basically, we went in really strong thinking we could very easily simulate it. And if we look at what we did at the beginning is we were doing more of symbolic things. So just a bunch of if-then, fuzzy systems, and you add more syllables or you add more features and, try to kind of use logic and simulation to figure out how humans would behave or to mimic that human behavior. Now, then we got a little bit more intelligent about what we were doing. And instead of just having expert systems, which is kind of what I think we were doing before, we got more statistical. So we were able to use things like information theory and inference. And inference, for example, is how we predict the weather or how other people predict the weather. I'm not regularly predicting the weather, but I also live in Southern California. So there's not much prediction of the weather required. You just know it's sunny and warm. Anyways, I digress. So, this statistical area kind of carried us along for a while. And from all of this development and research, we got some different uses. So what I'm showing here, I'll talk about, but what I wanted to show from this page is really the different uses that we have. And to me, there are kind of 5 different areas of uses. So there's areas around speech, of course, right? You've seen things like speech to text or text to speech. Maybe you've seen like the voicemail transcriptions in your phone, or you've been able to use something like Google Translate to translate different messages from different languages into your language. That also goes along well with language, where you might see, you chat with a bot or a customer service bot for an airline or something, and they're able to understand kind of what you're saying and respond accordingly. You also think about vision. So, when you are able to scan a QR code, or you're able to kind of classify images. So take a picture of something and, it's able to label that as, oh, this is a dog, or something like that. So there's lots of spaces where, artificial intelligence comes into play. And the reason I like to mention Azure Cognitive Services, which, by the way, this is a list of the Azure Cognitive Services. The exception is the search APIs. These are technically APIs now. I don't think they're part of the Azure Cognitive Services, but along the same ideas, this is something I call applied AI, right? And the reason I say that is because all of these exist as APIs for you to use. And in certain cases, there are APIs that you can customize. So we'll talk through a few examples, but this is a great way of just being able to apply or use AI. So I can use the computer vision API in my application today without having to actually know a lot about what's going on, because all of these APIs, all these models underneath have been developed by Microsoft Research for years and years and years. So that's good. For a lot of use cases, we'll talk about some. This is exactly what you need, and you don't need much else for that. Now, before the first demo, I want to give like a little bit of primer. Again, we're looking at all of this through the eyes of a data professional. So a big way that I'm going to show you for leveraging these technologies with SQL Server and Azure SQL has to do with machine learning services. So we've had machine learning services in some capacity since SQL Server 2016. We support Python, which you can see I'm a big fan of Python. We also support R. And in SQL Server 2019, we kind of released this language extension thing where you can kind of bring your own language extension. But with that, we released support for Java. And so you can see, the opportunity for .NET exists there and other things exist there. I've seen some people do things with F#, which was interesting. But basically how it works is that we can do in database machine learning with SQL Server and with Azure SQL Managed Instance. And what this means is you don't have to move your data anywhere. So that's a big benefit, honestly. It's a lot less effort to move the data, a lot less time and processing and expense. Just do the machine learning, do your analyses on the data where it lives. Now, some people were concerned about this, so I just wanted to throw out this architecture and say that it is actually run through a Launchpad service that launches satellites and then is able to directly communicate with the database, but it's not actually able to kind of manipulate or do too much there. We keep it separate just in case you have some bad actors or any corruption or anything like that. And the great thing is you can interact with all of this by just using T-SQL. Now, you can choose if you want to write the code in T-SQL and just bring it in there, or if you want to do it all in your language of choice, that's really up to you. So now let's switch over to a demo. I'm just going to show you a quick example. I'll share all these notebooks with you at the end of the session so you can try them out yourself, implement them yourself, or just even spend some more time looking at them. But for this first one, I'm going to bring up Azure Data Studio. I think at this point, hopefully most of you all are familiar with this tool. Azure Data Studio is a great cross-platform tool. We forked it from Visual Studio Code, and my favorite part is this idea of notebooks because we support different kernels, and then you're basically able to attach it to a database or a SQL Server instance, or where you can work on things like Postgres and other things like that. But it allows you to combine text and runnable code cells. And a great thing about those runnable code cells is the results are stored and then you can share them as you might like. So I have a few examples here of applied AI. So here I'm basically leveraging cognitive services that exist to do various things. So one example I have is sentiment analysis. And now for the examples in here, I was using the Java extensibility. So everything you'll see kind of is attached to a Java program. Again, all that code is in my GitHub repository. But what we have is sample, we're using wide world importers. We have some product reviews. And the use case here is we want to understand very quickly if people are giving us good reviews or not. So a good way for us to do that might be with the text analytics cognitive service. So basically what I've done is I've created a Java program. It's stored in this jar file compiled here, and it basically calls that cognitive service API and returns the result. So now I'm able to leverage this T-SQL capability called execute external script. And I basically say, okay, the language is Java. Here's where that package is located. Here's the data I want to leverage, and kind of give me the sentiment score as a result. And if you can see that the cognitive service is able to create that sentiment score for me. And remember, I didn't have to know that much about data science. I just wanted to know that I wanted to find sentiment and I wanted to analyze the cognitive service. So that's pretty cool. You can just use kind of out of the bat. Now, there are some customizable cognitive services. Again, I don't want to spend too much time here, but I just wanted to call out one that I find particularly fascinating, and that is LUIS. It stands for Language Understanding Intelligence Service, I believe. But you can use this. It kind of has a base natural language processing model, and then you can customize it to your use cases. So I can very easily, it's mostly done through a GUI. I can go in and I can add sample statements and I can label them. So I can say, oh, this was the destination, this was the time, and then I can train with very little effort a custom model. So very cool technology. Definitely go check it out. The URL for that is just luis.ai, I believe, or you can use your favorite search engine. But one use case I thought of is, let's say we have a trucking company. And in this trucking company, the drivers are required to log different statuses of where they are across their journey. Now, the statuses that they log are free form. And so if we look at what some of those might look like, someone says, headed to Houston from Detroit, Sunday, 12 p.m., from New York to Atlanta, Monday, 3 p.m., Seattle to San Francisco, Tuesday to 5 p.m. Some people say noon. You can see there's like different ways they're saying destination is Miami at 4 p.m. Sunday, beginning in Chicago. So lots of different ways truckers might be saying their status of where they're going and when they expect to arrive and where they're coming from. So similar to before, I created this custom language understanding model very easily through a GUID. And then I was able to kind of package up the call. So basically all this Java program does is call that Azure Cognitive Service LUIS and return the result. So I was able to package that up. And then again, I won't spend too much time here, but the model is basically able to extract the destination, the origin, and the time. And even notice for things like at noon, it's able to figure out what noon is. It's able to recognize these different destinations. So again, this is a way you can apply AI without necessarily knowing a ton about what's going on under the hood. So I just wanted to mention cognitive services. And I think it's a great example of artificial intelligence and a way you can kind of apply it as a developer or to some of your data investigations or analyses that you do. All right, so now that we've talked about AI, the next thing I want to talk about is machine learning. And we kind of have this formal definition for machine learning, which is kind of confusing, but basically what it says is a computer program is said to learn from an experience with respect to some class of tasks if its performance improves with experience. So again, this is a little bit confusing. So I like to look at a specific example. So let's say we want to teach a machine. This is my machine, my orange little robot. We want to teach a machine to learn how to identify if something is a cup or not. So what we're going to do is we're going to give it some data. And this is called labeled data because we know if it is a cup or not, right? So we're giving it some examples to learn and we know what the answer is. This is also called supervised learning. Supervised learning just means like we know the answer. And so that helps us in training a model or a machine to also learn what the answer is. the other kind is non-supervised or unsupervised learning. We'll talk a little bit about that later. All right, so what do we have here? So what we have in our data set are features. Okay, these features are really just columns that contain information about each of our sample data points, right? So we're talking about a cup, right? So does it have an open top, closed bottom, holds liquid, hand-sized? Those are our features. And then again, our label is it a cup or not? So what we did in this case is we have taken the images out of the data set, but just for a reference, we can say like, these are the sample images. So the first three are cups, and you can see they look different. The handles are in different places. Some you can see the liquid, some you can't. They might not have liquid in them, but you can see those features that align to each of those. And then when you look at the cat, which is the fourth image, you can see it doesn't, those features are different, right? So we send this to we leverage a model and we go to train the model, and the trained model spits out, something like this. Say, if it is an open top, has a closed bottom, it holds true, and it's hand sized, then it must be a cup. So then what can happen after we train the model is we can show it a cup it hasn't seen before or not a cup. And it's going to leverage whatever model it's come up with. It's going to leverage that and decide if it's a cup or not. So in this case, our model says it is a cup, and we're 90% certain. So it will give you some sort of, certainty score. So that's something, this is, kind of the most basic example of machine learning. And in this case, it's really a simple if then, but it could be much more complicated. Now, this is a group of machine learning known as classification. So we're trying to classify objects. So we know what the label is, and we're trying to predict it on unknown items, right? So if we were going to train this, I see a funny comment. It would be interesting, if not frightening, to see the machine determine the kitten is not a cup. Well, the thing is, it shouldn't be frightening, hopefully, right? Because what we've done is we've given it a bunch of examples, and then we're just trying to understand, we're trying to teach it. We're saying, so here's how we do. We get a bunch of data, right? And we would split that data into training data and testing data. And on that training data, it might look something like what you see on the screen here. And we basically train the model. So we'd say, hey, this cup has an open top, closed bottom, holds liquid, hand size, it's a cup, true. Just like you would have a baby and you might show a baby a bunch of cups, maybe not a baby because babies might not be able to tell you if it's a cup or not, but a toddler or a small child that could tell you, you could show the toddler a bunch of cups and a bunch of things that are not cups. And then after all that, you would hope you'd look at the child or small toddler and say, is this item like this? Is this a cup? And it's something they've never seen before, and they would be able to tell you if that is a cup or not. Okay, so that's classification. I digressed a little there, but that's classification. There are different use cases and algorithm families. So let's walk through kind of the 5 questions that I think data science can answer, or machine learning specifically. One is how much or how many. Sorry, these questions are funny. If the machine had to gather the data, it might try pouring hot coffee on the kitten. Yeah, I love that we're having some fun here. Nobody wants hot coffee poured on a kitten, though. I think we can hopefully all agree that, even though I'm team dog, I think I can agree I don't want hot coffee poured on a kitten. Yeah, of course. Thank you for the humor and bringing the energy. Okay, so let's talk about the questions that machine learning can answer. So the first is how much or how many. This is known as regression. You might see this as forecasting. Basically, you end up, at the end of the day, you're trying to predict a number. All right, now we have anomaly detection. So the question we're trying to perceive here is it odd? So a great example of this is if you have, your bank transaction. So every time I swipe my credit card tries to identify if the purchase I just made is fraud or not, right? So it's looking for if it's odd, if it's different from my normal spending habits, or if it's something that I would probably buy. So that's an example of anomaly detection or answering the question, is it odd? The next one is which category, so classification. So this goes back to our cup or kitten example. So at the simplest level, is it a cup or is it not a cup? But this can get more complicated, like classifying things like you see here into tools, birds, bikes, etc. I'll show you there's this very big data set called the MNIST data set, which folks are constantly trying to create better models for, but they're essentially trying to classify images. And that's what a lot of these things that you do when you take a picture and it's able to tell you what it is, that's what's happening behind the scenes, is a classification. Now the next is which action should be taken next. And this has a lot to do with like reinforcement learning. And the best example I have for this is like I have a dog, and when I want to teach him something, a lot of times it is reinforcement learning. So I teach him to sit, teach him to sit, teach him to sit, teach him to sit. And eventually he knows, like when I go like this or I say sit, I want him to sit. So I'm just using reinforcement. This is kind of similar, except using machines and not me and my dog. The last one is usually around unsupervised learning. So this is where you have a bunch of data and you don't have an answer, and you're either trying to find groups that go together, so you're trying to cluster things, or you're trying to recommend things. So this is like when I make my daily trip to Amazon and buy something. Amazon also suggests things I might also want to buy. Sometimes it's right and sometimes it's not, but here it's using that clustering or recommendation models to kind of say, oh, people like Anna that bought dog treats also bought dog bones or dog toys or that sort of thing. So these are the 5 main algorithm families and kind of classes of machine learning. All right, so now let's take a break from the slides and take a look at an example of machine learning. And it's Friday afternoon. Well, for me, it's literally just Friday afternoon, just barely afternoon. But for everyone else watching, like you've been doing a lot of work all day, it's almost 5 o'clock. So I thought for this machine learning example, we would talk about some wine. So there's a ton of free data sets out available on the web. So I definitely recommend, like, the best way to learn machine learning data science, just go pick a data set and get hands-on with it. So this is a data set I picked a while ago, the wine quality data set from this repository. You can see it contains different quality ratings for some red wine samples and some white wine samples, and it's based on the features. So again, these are the things that are used to make the predictions, is the wine's physical and chemical properties. So we're going to see if we can kind of predict the quality of wines. Now, one thing I'm going to use here, again, I'm not going to spend a lot of time here, but there are some awesome packages that Microsoft has developed actually through RevoScale Analytics, a company Microsoft acquired a few years ago. RevoScale Pi, RevoScale R. There's also a package called Microsoft ML. You'll see it in here somewhere. But these are great packages that help you to do distributed machine learning in database. So very powerful stuff that we have here. So here I'm just bringing in some of those packages. I'm not going to show you all how this works exactly, but basically we're able to do in database machine learning without bringing that data out and having to do it, like for this example, like processing it on my laptop. We're able to do it in the database wherever that database may be. And that could be Azure SQL Managed Instance, or it could be SQL Server. All right, so the first thing that I'm going to do, again, if we think about the team data science process, it applies to machine learning. I'm going to take a look at the data, right? I'm going to explore the data, and it's important to not just look at the numerical values or the statistical values of the data, but I also want to plot and look visually at the data. There are some data sets you can look at that will have exactly the same different, types of stats, but then they look entirely different. So what I'm going to do is I'm going to look at that data. And I will share this notebook, but I'm not going to go too deep into the code. And I might make some observations here, right? Like, wow, we have a lot more white wines than red wines in this data set. So maybe we're going to be able to more accurately predict for white than red, maybe not. I also noticed we don't really have any excellent wines in our data set, which is, disappointing, and also just something good to know as we start to look at what we're going to be predicting. Seems like we have kind of a lot of kind of medium quality wine. So this could be good, this could be bad, this could make it hard for us to kind of discern between like a 5 and a 6, but we'll see what happens. So after we've kind of looked at the data and we've understood the data, the next thing to do is to go ahead and create a model and train a model. So at the simplest level, we're going to split our data into our training and testing data set. Usually you want more training data than testing data, but you want to make sure you have enough testing data because otherwise you might be overfitting your model. Not something we're going to talk about today, but it's just something to keep in mind. So once we do that, we can go ahead and start to do some modeling. So what I'm using here is one of those RevoScale packages, which is readily available. And I'm basically saying I want to predict quality based on all the other columns. And I want to use the RX fast trees, which is basically a way to do something similar to a random forest. Again, not super important here, but basically we're going to train the model with an algorithm that is doing some sort of regression. So again, we're saying how much or how many. In this case, we're predicting a quality, but that quality is a number. So we can make some predictions. We can say after just doing not that much analysis, this is the actual quality and this is the score. So you can see, we're kind of off on some, but we're pretty good on others. And then after you look at you train your model, you want to look at the accuracy of it. You want to look at some various properties about how it performed. And one of those is an R-squared value. So actually, the higher R-squared value, the better. Some models will have, 95% for your R-squared. That would be an extremely good model, but you might be concerned that it's too good. I think more realistically for real world scenarios, getting like 70 or 0.7 R-squared or 0.8 R-squared is going to be great. This 1.4 is pretty low. So, the next step would probably be, can we find a better model? So can we do some tuning? Can we figure out which features are better? But for the cases of this, we're just keeping it simple. Let's say we're happy with the model. So now that we've created the model, we need to deploy the model back into our database. So we can basically leverage stored procedures to add this model to our database or to our SQL Server. And there are some tools to do that. Again, the purpose of this is not to teach you how to do that, but we're just giving you a look at some of the examples and showing you that it is possible to do it with things like Python or SQL or R. So that is machine learning in SQL. So we've talked about artificial intelligence, the biggest circle. We've gone a little bit narrower and talked about some machine learning. And next, we're going to spend the rest of the time talking about deep learning. So why do we need deep learning? We've seen, and maybe you haven't necessarily seen, but a lot of machine learning models can do things like predict that this is a dog, right? Now, the challenge is a lot of times, like, the dog could be in a different image, maybe the dog's standing up. There's so many different breeds of dogs that, like, it can get complicated to kind of predict and classify, especially images. Same with audio. It can get complicated, right? So one example of this, and just a side note, Buck Woody, who I'm sure a lot of you all know, he's a great guy. Buck and I do a lot of data science stuff together. We also have traveled very much together for work-related things. But one trip we had was to South Africa. It was a long, long time ago. But we managed to go on a little safari, and we saw this picture. Buck took this picture. And, it was really hard because in this picture are a bunch of wild dogs, but, we couldn't find them. And it took us a very long time to kind of zoom in around and looking around to see that, oh yeah, there are like a bunch of dogs right there. We just didn't see them. So if it's very complex for us to identify that there is a dog there, it becomes complex for a machine learning model to kind of identify these dogs as well. And this is just one example. This can be translated to any number of vision or text understanding types of things, like for example, like cancer predictions, like some of these these predictions and the data that you're looking at is so vast and so complicated that it can be very difficult for like a standard machine learning model to get good at identifying whatever it is that it's trying to do. So this is just one use case. There are many use cases for this. Image recognition, vehicular object detection, so what Tesla is doing or what other companies are doing with autonomous vehicles. So being able to manage that is very complicated and uses a lot of deep learning. I talked about some medical image analysis, mapping. So if you use like Google Maps, Bing Maps, Apple Maps, whatever, a lot of that is using deep learning to kind of understand the best route, to understand traffic and take all of these different data points in and understand them and then make a prediction on what the best thing to do is. Lots of other things like how your news feed, if you're using Facebook or Twitter, how that news feed is established. A lot of these complex use cases are leveraging machine learning. So now that we've talked about some of the use cases, let's break down a very simple but a very popular example. A very popular example is this data set that is available for free that includes a bunch of handwritten digits. So this is just one example of one sample, basically, of one of those handwritten digits. You can very easily see that it is the number 8, or at least I hope you can very easily see it's the number 8. But what a machine has to do is much more complicated. So it's very standard to kind of separate out this image, and we turn this image into basically an array of numbers. So what you see here is we're giving it a brightness scale, basically. So this is 0 to 255. That would be 0 is black, no light, and 255 would be very much light. So you see where the 8 is, those numbers are higher and closer to 255. Okay, so then once we create this array of numbers from the image, what we do is we turn it into one long string, and each one of those pixels, so there's 784 in this example, each one of these pixels becomes a feature. Now remember when we did the is it a cup or not sample, we just had 4 features: open top, bottom, closed bottom, holds liquid, I can't remember what the other one was, has a handle or something. But now we have 784 of these. And that's just for a black and white image. If we had a color image, there are 3 layers of these, right? So we have 784 times 3 pixels because we have a red layer, a blue layer, and a green layer. Those are the way that images are structured and stored. So for this, what we're going to do is we're going to take each pixel as a feature. So think of it, we've got all of these columns like you saw before. We're going to use all of those columns to help us predict, is this the number 8? So we're going to feed those into our neural network. So this is a great example of how like the computation is heavy and the amount of data is very large, right? Because there's thousands of images that we're analyzing like this, and each one has 784 pixels. And yeah, this is not a kitten. That is correct, NJ. Okay, so let's talk about how deep learning works, and we're going to learn through layers. And I'm going to try to break it down. I'm going to gloss over some of the math, but I'm going to try to keep it consumable so you all follow along. All right, so this is a very simple, what we call a 2-layer network. Essentially, like the first layer, the input layer, doesn't really count, but we have one hidden layer and one output layer. So we call this a 2-layer network. Now, what happens in the input layer? I'm going to take you back to maybe middle school or primary school math. Somewhere you learned the equation for a line. So think to yourself if you remember that equation for a line. Some of you are closer to that age than others, but that equation for a line is y equals mx plus b, and m is the slope and b is the intercept. So where it crosses the y-axis. Okay, so this should look very familiar then. It does and it doesn't, right? Let me grab my laser pointer. But this is our x, this weight is our m, and then we're going to multiply them together, and we're going to add b. Now, actually, in this example and the example I'm going to show you in a second, we're not actually going to use the b. We're just going to forget the b. But a lot of times you do actually want to include this b. It's very important, this intercept. But this is our mx, right? Our slope times our input, and that's going to give us the y. A little more complicated than that, because what we're going to do is we're going to assign random weights for our input layer, and there should be the same number of weights as there are in our earlier example as there are pixels, right? So we're going to have this random number of random assigned weights. So like weight 1 might start as 0.1. Weight 2 might start as 0.47, right? Just random numbers. And what we're going to do is we're going to multiply these numbers together, and then we're going to sum them all. So that's what this is doing. It's a sum of each x multiplied by each weight. This is also, if you remember your matrix multiplication, this is known as the dot product, where you multiply each individual item and then you sum them all together. So basically here we're doing the dot product and coming up with that sum. And then we're going to use an activation function. So what we've done is we've gone from here and we're trying to get to here. So we took these 3 incoming weights, we multiplied them by their inputs, and we summed them together. And then we're going to use an activation function. And what an activation function is, that's the dot product, but what an activation function is basically there are a few different ones, but here we're going to use a sigmoid, and think of it kind of like a light switch. It basically takes a value and pushes it between 1 and 0 and makes it very close to 1 and 0 and not a lot in between. You can see there's very little that goes between 1 and 0. At the ends, it's 1 or 0. So we're basically turning on or off a switch. So based on what happens here, we're going to run the activation function, in this case a sigmoid, and get an output. And so that output should either be close to 1 or close to 0. So we're basically turning on and off switches. So that's just how we get this one item. And so we're going to do the same process for this item, for each node in each layer. And then we're going to use those as the inputs into the next layer. So now we have a whole new set of random weights here, and we're going to multiply it by the inputs. Again, we're going to sum, do the activation function to turn on or off that switch, and that's going to give us an output. So that process is known as feed forward. So we go forward through, so we're going this way. I think I actually have an animation for that. Oh, no. So we're going to go this way through the neural network. And we're just doing that one time. That's all we've done so far. Now, the next thing we're going to do is we're going to try to update our weights, because since they were randomly assigned, they probably aren't very good, right? So we're going to go back through. So we're going to go this way, back through, and it's called back propagation. So we feed forward and we back propagation. And during that back propagation, what we're trying to understand is how wrong were we, right? How off were we from what this was supposed to be? That's what we're trying to do. So the first thing we do is we're going to find the sum of squares loss. So we're going to say, okay, how wrong were we? And that's a good data point for us to have. And then we're going to say, how is the loss changing, right? So are we going towards more loss, or are we going towards less loss? And how can we update the weights so that there's less loss? And the way you can do that, and if you remember, if we go back to calculus, when we talk about how something is changing, that's also known as the derivative, right? The derivative is kind of like that m value we talked about, the slope, right? How is it changing? So what we're basically going to do is we're going to take the derivative of our loss function, and this is basically the actual minus the what we came up with, and then squared and then summed together. So that's how we're classifying loss. So we want to know how loss is changing. So we have to take the derivative of this function. And now the derivative of this ends up giving us how is loss changing. And that's where the math gets a little hazy, and I'm not going to spend too much time on it, but I do have lots of articles in my resources. So if you want to dive into this math, you can. But basically, we're coming up with the derivative of loss. And we're going to use that derivative of loss to update our weights. Each weight is going to have a new one. We're going to take the old weight add the derivative of loss, and that's going to give us the new weight. So we're going to go back through the layer. So let's say we start here. We're going to go this way to this layer and figure out how is loss changing, derivative of loss. And then we're going to take that value that we come up from here, add it to the weight that was assigned here, and we're going to update that weight. Now we have a new weight. So we're going to do that for this one, and then we'll do that going this way. For this one, we'll get a new weight based on the derivative of loss and the old weight that was coming into this one. We're going to do that for each node going backwards to each item to update all of our weights, right? So this process is known as back propagation. So two big parts: feed forward. We go through and see how our model performed, and then we use that to go back and update our weights. So we will feed forward, we'll back prop, we'll feed forward, we'll back prop, and we'll do this lots and lots of times. And this is, again, very simple neural network, but there's lots of different things you could be doing in the layers. Okay, all that being said, I want to get into the demo and show you how this plays out. So you'll see some of these things. Again, you can play with these notebooks yourself. We're basically defining our activation function, which is a sigmoid, again, turning it on and off. And then we're defining the derivative of that loss. So I'm going to skip ahead and show you what we're going to do. So first, we're going to define our neural network. We're going to say this neural network has two layers. That's why we have two sets of weights, weights 1, weights 2, just like you saw in the diagram. And we're going to set those to random numbers, just like I said. So we're starting with random weights. We have our input, we have our output, and basically we're setting up the shape of our output to be the right shape. Next, we're going to feed forward. And again, this is a 2-layer network, and we're assuming that the bias is 0 or that B value is 0 in our MX plus B. And so we're essentially doing the dot product. So again, we're multiplying the input by the weights and then summing it together. So that's the dot product. And then we're using the activation function to turn that switch basically on or off and get a result for layer 1. We're going to do the same thing between layer 1 and our set of weights 2, do the dot product, take the activation function, and get the output. So that's pretty simple, our 2-layer network. Now, the next step was our back propagation. So we're going to find the derivative of loss. And that's what we're doing for here. We're doing the derivative of loss of weights 2 first, because again, we're going to go back through the model. So we're going to do weights 2 first, and then weights 1. And that's what you're seeing here. Again, not going to go into the math of this right now. And then we're going to take the derivative of loss and add it to our existing weights to update our weights. And so every time we call this neural network, we're going to feed forward and back prop 1 time. All right. So now let's talk about an example. So let's assume instead of handwritten digits, we just have these images. And what we want to do is we want to be able to predict with the neural network which image has an L in it and which one doesn't. So image 2 is not an L, and image 3 is not an L, but the other images are L's. Very simple. So we have to turn these images into an array of numbers. So what I'm going to do is I'm going to make them into pixels. This is much smaller than the other one you saw. It's just a 3 by 3. And basically we're going to label it a 0 if it's white, a 1 if it's blue. So this would be 0, 1, 0, 0, 1, 1, 0, 0, 0. And you can see I've kind of done that for each of these images here. Now what we're going to do is we're going to use this to create a single array. This is sometimes called a tensor, which might be why you've heard TensorFlow before. But we basically create this tensor, and you can see here I've stored it. We're using Python here. And you can see we have the full set of data, we have the features, and we have the labels. So we have everything that we need for this model. Now, what we can do, since we already created that neural network program, we can just say, okay, we're going to create the program with X and Y. Remember, X is our features and Y are our labels. So Y is what we're trying to predict. And now what I can do is basically with very simple Python code, I can say, hey, for 400 times, basically do feed forward and then do backprop, right? For this neural network we've defined with our X and Y values. And then let's print the results and the confidence. So what we're able to see is the neural network predicts with high confidence, pretty high confidence, that image 0, 1, and 4 are else, and pretty sure that images 2 and 3 are not else. So if we go back up, you can spend some more time on this later, we can see that image 2 and 3 are not else, but image 0, 1, and 4 are. So this is a very simple example of a neural network. I hope you all will spend some time looking at it and learning more about it. And again, I'll make all these notebooks available to you. Now, the next thing I wanted to say is, like, there can be multiple hidden layers, and there can be lots of different things happening in these layers. Like, we can decide to turn every other node off in a layer. We can decide to add a filter on a layer. Lots of things we can do. But depending on how you build your neural network, these layers can start to represent features. So remember, we talked about what features are. But for example, you might be able to see edges or combination of edges. So you're seeing edges, you're seeing like some different facial features, and then you're able to see like actual faces being stored in the model. And I'll share a reference to this really interesting article where they're actually visualizing some of the different layers, what they produce in the model, and then trying to find what images those relate to. So for example, if you look at this one, you can see it kind of looks like maybe there's some chains in it, right? Or you look at this one and there's a bunch of arches in this layer. And you can see, like, for example, I'll just give one example. For this arches one, you can see, you know, maybe this would help the model in identifying if the image has arches in it. So this is a very fascinating and just cool to see what is created and how they visualize it. So I'll share a link to this in the deck. Now, I know we just have a few minutes left. So finally, I just wanted to say, like, there are lots of tools and platforms available for you. So we talked about kind of the pre-trained cognitive services you can just apply AI with. We didn't talk a ton about frameworks, but there are a bunch of different frameworks that you can use. And I'll share some resources if you want to go get hands-on with some of these for free. We have some different services. One is the machine learning VMs. These come built in Azure. They come built in with different tutorials, different packages, different tools that you'll need for data science. You might be able to search for them, called a data science virtual machine, or a DSVM. We also have services that can help you with machine learning processing power, as well as Spark-based things like Azure Databricks, big data clusters, Azure Synapse. And then we have different hardwares, not just Microsoft, but in general, there are different hardwares that allow you to do this at varying scales. And I talked a little bit about SQL Server already, how this plays into the picture. One last thing I'll land on for that is that you're able to kind of train anywhere and deploy anywhere, and that's a really great benefit of Azure SQL and SQL Server. So, you know, I could train on-prem with my huge set of data that I have on-prem, and then I could deploy to my Azure SQL database, you know, to use for my applications. So we've done a lot in not a lot of time. If we were in person, I would go through and do this pop quiz. It's kind of a lot of fun, but just in the sense of time, and that I can't like call on random people and ask them what they think the answer is. You know, this is kind of a review of the different things that we talked about today. I hope this was useful. I have some resources for you all here. So I will leave this screen up. The one thing I really wanted you all to end with is two things, actually. On our Azure SQL YouTube page, Buck Woody and myself have been doing a series on machine learning and data science, and it's a really fun series. So if you're interested in learning more in a casual, fun way, that's a great series to check out. The other thing I wanted to mention is if you Google or Bing the 30 Days to Learn It, this is programmed through Microsoft Cloud Skills Challenge. And basically, if you're committed to learning more about data science, or you're committed to learning more about artificial intelligence, you can come to this page and you can basically register for a certain program. And you can pick, if this is the topics you're interested, you can pick either the Azure AI Fundamentals, or you can pick the Azure Data Scientist Pass. And this basically gives you free hands-on learning experiences to learn on your own. And then if you complete all of the learning that is kind of hands-on on your own, you can get 50% off getting certified. So now not only have you taken all the learning requirements, but you've gotten certified and you've done it all in 30 days. So I think it's a great thing to do. So, regardless of how much you learned today or whatever you want to get involved with, this is a great resource. So the easiest way to find it is to just Google 30 days to learn it. The code for everything, all the notebooks are in analytics. If you look in the SQL ML folder, and I know I'm a few minutes over, so I apologize. I thank you so much again for joining me, and thanks again, Mala, Kathy, for this opportunity. It's been a lot of fun, and I hope it was useful for y'all too. If you have any questions or anything you want to chat about, please feel free to reach out to me. And with that, I will pass back to the host.